Yeah, so why is the warping path interesting? Well, the warping path gives us obviously, or the length of the warping path gives us the dynamic time warping, because we can now have, of course, a couple of warping paths here that fulfill these properties here. But of course, we look for the one that have the minimum cost. Yeah, so we're looking for the cost minimum warping path. So let P denote the set of all warping paths that satisfies those four conditions here. The size of this set here is exponential in n plus p. Of course, we can compute or define the cost by simply summing up all the differences here, if we have the corresponding DTV instance here, and the actual dynamic time warping distance can then be computed as the length of cost minimal path between those two time series here. Yeah? Computing the dynamic time warping distance comes down to compute one cost minimal path among all those warping paths here. Yeah? Just a comment here down here. So for time series with the same length, the warping path, which just has 1, 1, 2, 2, 3, 3, 4, 4, up to n, so the warping path length is n, yields the Euclidean distance. Yeah, because we just sum up. So the cost is just the sum of the corresponding values, of course. Yeah, so we would, in that case, have as a cost of this path here the cost of the comparison of the first element in x with the first element in y, the second element in x with the second element in y, and so on and so on, and the nth element compared with the nth element in x with the nth element in y. And if you sum all that up here, like this one here, you will get obviously the Euclidean distance in that case. Yeah, so that is the special case. So Euclidean distance is the special case of dynamic time warping if you have no warping, obviously. So that is the basic point, that you have no warping here. But anyway, the general case, of course, is that you allow warping. Yeah? So the warping path has length more than n, n plus m plus 1 in the worst case, so to say. Yeah? And yeah, if you allow warping, and that's the basic idea of dynamic time warping, of course, then you have this, where is it here, this basic recursive pattern. First of all, of course, you can do that by computing the optimal alignment and taking the length of, or the cost of these of this cost minimal alignment. Yeah, and well, how to compute that? Well, the same way as in case of dynamic of the edit distance, of course. So here, if you just take the recursive computation of the dynamic time warping distance, you are again, surprise, surprise, in O of 3 to the power of n plus m, yeah, because you have potentially in each call you have 3 recursive subcalls potentially in the worst case. So in the worst case, you have 3 to the power of n plus m calls that you have to compute, and of course all of many of them are again redundant. So yeah, looks similar to the edit distance, absolutely. So it's exactly the edit distance that we do here, more or less. Yeah. So a better way, of course, is to compute the dynamic time warping distance by dynamic programming. In order, well, what you do is, with the dynamic programming scheme, you compute this cost optimal path here, yeah, and you can do it the same way as before in the edit distance example. So that also sounds or looks very similar to you. Well, one caution here. The matrix for the optimal alignment here now looks a little bit different, because in the edit distance we started at 0, 0 top left and walked down here to the lower right corner. Now here it's a little bit different. 0, 0 is this one here, so the lower left corner is 0, 0, meaning that the blue one here, the left time series here, is displayed from bottom to top. rather than from top to bottom, which we did in the added distance visualization. So just don't get confused here. It's really the same idea and the same concept. The only thing is that we don't start here and go down here. So we start here and go up here, right? Yeah. So analogously to added distance, any path between any alignment path, any warping path between x and y can be expressed as a path in this matrix here, and the size of the matrix, of course, is given by the size of the length of the two corresponding sequences or time series here, n for x and m for y. So it's an n times m matrix. Yeah, and we use again dynamic programming to compute this cost optimal alignment path, warping path, basically. Yeah. We don't go into details here because it's really exactly the same as before. Just that you know some properties. Dynamic time warping is usually not a metric. We discussed whether or not this is really important already a couple of times. But anyway, dynamic time warping is in that case not a metric because it allows the replication of elements, and that leads to some properties which are properties that somehow deny the metric properties. For example, we have no identity of indiscernibles. So here you see two time series x and y, and the dynamic time warping between those is 0 because you can match this one to this one here, which gives you 0, then this one to this one 0, this one to this one 0, and then this one to this one 0, this one to this one 0, this one to this one 0. So you get all zeros. Summing up a lot of zeros gives you 0 here, even though, so the distance between those two is 0, even though those two time series are not exactly the same. Yeah. So a metric says that only if x and y are the same, then the distance should also be the same, is 0. Yeah? Or the distance of 0 means or is equivalent to the fact that x and y are the same, which is obviously here. This is a counterexample for that. And if you know it a little bit more, so also the triangle inequality does not hold. So here's an example for where the triangle inequality does not hold, because we have here the dynamic time warping distance between x and z. So here is no real alignment that you can have. So you can just map everything to everything like the Euclidean distance here, which gives you 15 between x and z. And that should be, if the triangle inequality holds, smaller or equal to the distance between x to y and the distance between y to z. Well, x to y is the same as before. That's more or less the Euclidean distance, which is 10. And from y to z, we have 1 maps to 1 is 0. 2 maps to 3 is 1. 2 maps to 3 is 1. 3 maps to 3 is 0, 0, 0. So we have just 1 plus 1 here. So these two actually are mapped to 2. Yeah. So we have the sum is 12, and that needs to be greater or equal than 15, which is obviously not the case. So here's another counter example why dynamic time warping is not a metric in that case. Yeah, and here's just a comparison between dynamic time warping and Minkowski distance, again taken from this very, very good tutorial from Eamon Keogh. So here there's a comparison of time series that measure the daily network traffic of a company, and you see that the normal days, so to say, are the normal weeks have 5 working days, and Saturday and Sunday is off. And then we have some weeks in between where we have public holidays on Wednesdays, for example, or on Fridays or on Tuesdays. And maybe we also have some weeks where we have 2 public holidays, and so on and so on and so on. So if you just apply Minkowski distance to this one here, you get, again, apples and eggs and oranges mixed up everything together. If you take dynamic time warping as a distance on those data sets, you will end up in several clusters. One cluster with 3 working days, a second cluster with 4 working days, and a fourth cluster with 5 working days. Yeah, and it's just because you can, regardless when the public holiday is actually, yeah, in all of those clusters here. Yeah, and that can be somehow counted through the dynamic time warping. So if you have a 4-day working week, then regardless if the public holiday is on Wednesday or on Monday or on Friday, you can warp along the time axis and see that you have these 4 peaks here for the daily network traffic in the company, and you can align that properly so that you don't care where this basically where this public holiday day was. Yeah. Okay, so that's it for dynamic time warping. Just one additional thing here, which is least common subsequences for time series. Well, we talked about least common subsequences for sequences, and of course you can, as a kind of variant or extension to edit distance, and since dynamic time warping is the edit distance on time series, you can also have least common subsequences, which is also again tolerant to gaps in the 2 compared time series. That could be especially interesting if you compare trajectories, yeah, time series of spatial locations that contain many outliers at the start, because all these trajectories follow in the middle some common path, but they have different start points and different endpoints. Yeah, for example, all the commuters to, I don't know, Kiel, they have to go through the Ostring. Yeah, so there will be a long time where all the trajectories have the same locations, but coming or getting to the Ostring requires different, so to say, routes, different trajectories from different starting points. And of course, getting out of the Ostring to, for example, the CAP skyscraper, or to I don't know, the Botanische Garten or whatever, again means that you left you left the Ostring and then go in different directions again. Yeah. So in that case, those least common subsequences as a similarity measure can help you again. Yeah? And that is the basic application scenario where LCSS makes absolutely sense.